everyone, so we're going to solve a problem about evaporation in heat and mass transfer. So the problem states that a 1.5 weight% aqueous salt solution is concentrated to 4% in a single effect evaporator. Feed rate of the evaporator is 7,500 kilograms per hour and has a temperature of 85 degrees Celsius. The evaporator operates at 1 bar. Saturated steam at 170 kilopascal heats the solution. Find the area if heat transfer coefficient is 2,500 watts per meter squared Kelvin and assume dilute solution. So we're given the data of the enthalpy of the feed, vapor, and the liquid. We also have the saturated steam temperature at 170 kilopascal, which is 115 degrees Celsius. So here is a diagram for the problem. So the feed entering the evaporator at 7,500 kilogram per hour and has a weight percent of 1.5% and has a temperature of 85 degrees Celsius. The vapor and the liquid exiting the evaporator, which is to be solved, and the weight percent of the liquid, which is 4%. And since it is mentioned in the problem that it is a dilute solution and the evaporator operates at 1 bar, so we can assume that the boiling point temperature is 100 degrees Celsius. We also have the saturated steam at 175 kilopascals, which heats the solution and has a temperature of 115 degrees Celsius. So we're given the feed rate, the weight percent of the feed and the liquid, and the heat transfer coefficient, which is 2,500 watts per meter square Kelvin, and the boiling point temperature, and we are to solve for the area. So the first thing we're going to do is to do a mass balance, which is F is equal to V plus L. And since we're given the feed rate, which is 7,500, so we're going to substitute its value there. So 7,500 is equal to V plus L. Since we have two unknowns, so we're going to need one more equation. So we're going to do a solute balance, which is feed times its weight percent is equal to L times XL. Vapor is not included in the solute balance since there is no solute in the vapor. So we're already given the weight percent of the feed and the liquid. We also have the feed rate, so we're going to substitute the values there. So 7,000 times 0.015 is equal to L times 0.04. And then we can calculate for the L, which is 2,812.6 kilograms per hour. And since we already computed for the value of L, we're going back to the mass balance to compute for the V. So 7,500 is equal to V plus the computed L, which is 2,812.6 kilograms per hour. And then the computed V is equal to 4,687.5 kilograms per hour. So since we already computed for the rate of the liquid and the vapor exiting the evaporator, now we can do the energy balance to get the value of Q external. We're going to need this value later on to solve for the area. So the feed multiplied by its enthalpy plus Q external is equal to V times its enthalpy plus L multiplied by its enthalpy. Since it was mentioned in the problem that we already have the enthalpy for the feed, the vapor, and the liquid, so the thing we're going to do is just to substitute its value to the formula. So 7,500 times 356 plus Q external is equal to 4,687 687 times 2675 plus 2812.5 times 419.2, and then we can calculate for the Q external, which gives us the value of 11,048,062.5 kilojoules per hour. And we already know that the formula of Q is equal to the heat transfer coefficient multiplied by its area and delta T, where delta T is equal to the saturated steam temperature minus the boiling point temperature. And we're going to convert the temperature from Celsius to Kelvin, so I already converted it. So 388 minus 373 is equal to 15 Kelvin. Since we already computed for the delta T, let's substitute it to the formula. But notice that the computed Q external is in kilojoules per hour and the heat transfer coefficient is in watts per meter squared Kelvin. So we're going to convert kilojoules to joules and hour to seconds. So 11,048,062.5 kilojoules per hour times 1000 joules per 1 kilojoules times 1 hour over 3,600 seconds is equal to 2,500 times area times delta T, which is 15 Kelvin. And we can compute for the area, which is 81.84 square meters. And the problem is done. Thank you for listening.
First and foremost, the topic for this discussion is a problem about crystallization. So before I begin, I'll be briefly discussing crystallization as a separation process to furthermore smoothen the problem at hand. Crystallization, on a general term, concerns with the removal of a solute such as salt from a solution by precipitating the solute from the solution. Crystallization as a unit operation have certain fundamentals and basic principles or mechanism in common. For example, the mechanism of diffusion or mass transfer occurs in drying, membrane separation, absorption, distillation, and of course, crystallization. So now, let's talk about the problem, which is the problem is a feed solution of 10,000 pound mass of 130 degrees Fahrenheit containing 47.0 pound iron sulfate per 100 pounds of total water is cooled to 80 degrees Fahrenheit, where iron sulfate heptahydride crystals are removed. The solubility of the salt is 30.5 pound iron sulfate per 100 pounds of total water. The average heat capacity of the feed solution is 0.70 BTU per pound mass times degrees Fahrenheit. The heat of solution at 18 degrees Celsius is negative 4.4 kilocalories per gram mole, which is equivalent to negative 18.4 kilojoule per gram mole of iron sulfate heptahydride. Calculate the yield of crystals and make a heat balance. Assume that no water is vaporized. So first, we will make a black diagram to further understand the problem. So for this black diagram, which is the crystallizer, there goes the mother liquor, the crystals, the feed, and of course the heat, which can be added or removed. And first, we make a basis. The basis is equals to 10,000 pound mass per hour feed. Early in the solution of most balanced problems, one should choose a basis of calculation. The basis is a reference you choose for the calculation you plan to make. And for the balances, first we make the total balance. Total balance, which is 10,000, is equals to S plus C, which is feed, is equals to the mother liquor plus crystals. Then, on batch balances, we consider iron sulfate balance. So for iron sulfate balance 10,000 times 47.0 over 147.0 is equals to S times 30.5 over 130.5 plus the C times 152.0. 152.0 is the molecular weight of iron sulfate over the molecular weight of iron sulfate heptahydrite, which is 278.02. So we use the total balance and the iron sulfate balance resulting on two equations, two unknowns, so that it satisfies the equation above to solve the two unknowns, which are C and S. The C is equals to 2,750 pound mass of iron sulfate heptahydrite crystals, and the S, which is the mother liquor, is equals to 7,250 pound mass solution. And then we continue for the heat balance. We first solve the heat of solution. For the heat of solution is equals to negative 4.4 kilocalories per gram mole times 1,000 calories per kilocalories over 278.02 grams per gram mole times 453.6 gram per pound mass over 252.16 calories per BTU, which is equals to the heat of solution equals to negative 28.47 BTU per pound mass of iron sulfate heptahydrite crystals. So the enthalpy H1 of the entering solution at the initial temperature, so H1 of feed, which is 10,000 times 130 minus 80, which is their temperature, times the heat capacity, equals to 350,000 BTU. So the enthalpy H2 of the final mixture of crystals and mother liquor at the final temperature is equals to heat of crystallization. H2 is equals to negative 28.47, which is the heat of solution, times the 2,750 equals to negative 78,300 BTU. This is for crystals. Solving for the total heat absorbed, Q is equals to H2 plus HV minus H1. HV is our water vapor. So it assumed in the problem that there is no water vaporized, so we cancel the HV. Q is equals to negative 350,000 minus 78,300, which is equals to negative 428,300 BTU. So the total heat absorbed Q is equals to negative 428,300 BTU. So since the heat absorbed is negative, our heat is removed. So if Q is positive, heat must be added to the system, and if it is negative, heat is evolved or given off. That's all for the problem on crystallization. Thank you.